All right. So today's focus is on rates of reaction. Um, this would be better exemplified by me as your teacher in the classroom. We have an experiment. I have an experiment that I like to do with this where we get to test the rates of the reaction. And the experiment that I like to do is it's one where you have old school film canisters and you put an Alka-Seltzer tablet with water in there, and you can basically just shoot these film canisters all around the classroom, and it's kind of a fun time for everyone involved. And then what we do is we change a couple of the different variables of the reaction itself, and we try to time and see what reaction is faster. So in some of the cases, we'll add more Alka-Seltzer. In some of the cases, we'll add more water. In some cases, we'll heat up the water or cool down the water. And the idea is you just want to change the circumstances of the reaction to have it be to see if it impacts how quickly the film canister will shoot off. So, in terms of that phrase, the rate of reaction, what that means is it's basically like the speed of how quickly some reaction is happening. Um, there's a whole bunch of different levels of rates of reaction. Rusting, for example, if you've seen that on a vehicle or on a really old piece of metal, that takes a really, really long time. That is not something that happens overnight. It takes a long, extended period of time for something to rust. Baking is considered a pretty fast reaction, but an hour to complete a reaction isn't that great. That is a pretty extended and long period of time. And then explosions, those would be reactions that would be considered very fast. Almost anything that happens in your body, those reactions can go way faster than even a simple explosion reaction like this. So, for an example, you digesting your food, that does take a little bit longer of a time. But let's say like a reaction of your brain communicating to the rest of your body that you're hungry, that reaction and that process is way faster than even an explosion is. So there's a wide variety of reaction rates. In terms of why some reactions are faster than others, there is a couple different reasons that that occurs. Reactions take place when the energies collide with a certain amount of energy, and that amount of energy is called the activation energy. So you can kind of think of it like laying in your bed, and you wake up at 2 in the morning and you need to pee. You need to have a certain amount of activation energy to pull yourself up out of said bed, walk over to the toilet, and relieve yourself. Otherwise, you'll just pee your bed. If you don't have sufficient energy to pull yourself out of the bed, you will end up changing your sheets that evening. There are two different things that influence the rate of that reaction: the frequency of collisions between particles and the energy with which particles collide. So, if we were in the classroom, this is the example that I would have given. We would have all put blindfolds on in the classroom and moved all the desks out of the way. And I would have had all of you try to run into each other with blindfolds. And you would have to collide in a certain fashion. And last semester with the grade 12s, what I said is when you find somebody, you have to put your hands on their facial cheeks, and they have to put their hands on your face cheeks, and that will be representative of a successful collision. And the idea is you have to be able to find someone, first of all, and then also have the right orientation or the right actual touching of each other to be able to react. And then what we would have done is I would have taken everybody except two people out of the room. So I probably would have left Enoch and Kiana in the room just for kicks. And then I would have said, okay, you two need to find each other. But what they wouldn't have realized is I would have put a whole bunch of barriers in the way, and it would have taken a really, really long time for them to find each other. And the idea would be is if there's less particles or if there's less of you guys moving around, a reaction takes longer. The other idea is if the orientation or if like the hands on the face cheeks, if I chose something that was a little bit more difficult to achieve, that would also make the reaction take a longer period of time. So this bottom sentence here says if particles collide with less energy than the activation energy, they will not react. The particles will just bounce off each other. So that would be like if I was blindfolded and I finally found Abby, but I had no idea because she's so short where her face cheeks were, I couldn't react with her and I'd have to go just find another tango partner for that reaction. Sorry, Abby, that was kind of a cheap shot. A low blow, if you will. Um, Anything that increases the number of successful collisions between reactant particles will speed up that reaction. What factors affect the rate of reactions? Well, increased temperature. If something's hotter, all that means is that the molecules in that actual substance are just moving faster. That's all that that means. If you think about solids, liquids, and gases, solids generally have really, really confined molecules, meaning they can't move around much, meaning it's a lot harder for them to find successful collisions. If we think about a liquid is confined to a certain region, and those molecules can move around and they can collide with each other. But in a liquid, generally speaking, the molecules are moving faster than when it's in the solid state. If you think about a block of ice versus water, when water is wet, when it's in its liquid state, the molecules are moving around a lot faster than when it's in a block of ice. And then obviously when we create steam, that's when the molecules can move as rapidly as possible, and that's where reactions can happen. So if we want to speed up reactions, we can increase the temperature. Another way that we can do that is we can increase the concentration of dissolved reactants and increase the pressure of gaseous reactants. And all that means is that if I have more of something, the reaction is more likely to happen. So that was the example of the classroom. So let's say that like there were only two molecules in this border. It would take probably a pretty long time for these two to find each other and eventually react. If there was a bunch of different molecules in the classroom, or a bunch of you guys in the classroom, it would be a lot easier to find someone else to collide with and to react with. The last one here is increased surface area of solid reactants. So if we think about this, let's draw a really poor cube. Let's say that that's an ice cube. Right now, the only places that can have a reaction occurring on this ice cube is anywhere on the outer surface. So if I were to smash this into a bunch of different pieces, what that would do is we would have the entire surface area of the outside of the cube, but also now the entire surface area of the inside of the cube as well, which would make that reaction go much faster. This is why, and we would have seen this in the reaction that we would have done. A lot of times, in order for reactions to happen faster, you crush stuff up. Trying to think of a really good example of that. I guess if you want to dissolve ice, for example, if you have ice on your driveway, generally speaking, you want to crush it up first, and then you want to pour your Deltzer, the salt that helps dissolve your ice on your driveway. Then you want to pour it after you've actually crushed all of the ice. Otherwise, it'll take a really long time for that reaction to occur. And then the last step here is this says the use of a catalyst. Let me just erase some of this stuff here. So this last one says the use of a catalyst. And a catalyst, the other name for that is an enzyme. And enzymes are what you find, generally speaking, in a living organism. So you have a lot of enzymes within inside of you. One of the ones you're probably the most familiar with is your saliva. That is an enzyme. And what that does is it helps you break down carbohydrates, so things like bread. It helps you break them down quicker. But the saliva itself and the catalyst or the enzyme, these don't ever get involved in the reaction, so they don't react, but they help the reaction go faster. So this then, I would extend the walking around the room blindfolded, help reaction go faster. I would extend the example of you walking around with blindfolds, and in order to have Enoch and Kiana find each other, I would have both of the Lukes guide them towards each other. And that's kind of what a catalyst does. The catalyst or the two Lukes aren't ever going to react themselves, but they're going to help the reaction go along faster. There is another kind of important piece of information, which is that reactions don't proceed at a steady rate. They start off at a certain speed and then get slower and slower until they stop. And that has to do mostly with the concentration rule. Let's say that there were 4 balls inside of this little box. It would be pretty easy initially for two of them to find each other. But once two of them have found each other and have collided with each other, now we only have two left over. And on the previous slide, I had said that that would take a really long time. So once particles or once molecules have reacted with each other, we kind of lose the opportunity or we lose concentration or the amount of reactants that can actually react. And so that's why they get slower and slower is because the concentration of them is decreasing. All right. In terms of temperature, how does that impact the reaction rate? Basically, what happens is as you increase the temperature, this is called the rule of 10. As you increase the temperature by 10 degrees Celsius, the reaction rate will double. So if I had a reaction that was occurring at 0 degrees Celsius, I could increase it to 10 degrees Celsius and the rate would double. I could increase it then to 20 degrees Celsius and then that rate would double as well. And basically what that does is if we have all of these molecules in a box, let's say we had those 4 molecules in our box, if I increase the temperature, what that does is it makes them move faster. So it accelerates those collisions that would have taken a little bit longer to occur. Kind of a good example of that is if you think about uh, the DVD symbol that moves around on those old school. This is a really good office meme, but the DVD symbol that moved around the TVs, you kind of sit there and wait until it hits just in the very, very corner. And it takes a really long time because the DVD symbol doesn't move very quickly. But if we could fast forward that animation, you would see it hit the corners of the screen with a higher frequency. Just because it's traveling faster, it's still doing the exact same pattern, but it's traveling faster. So the amount of times it hits the exact corner will be increased. The other thing that this does is it gives them more energy. I said that the two things necessary for a successful collision were the orientation, so the way that they're facing each other, and the amount of energy that they collide with. And so the number of successful collisions, because we're speeding them up, will increase. Another good example of this would be like if you were playing billiards or if you were playing pool and you had to hit the white ball and you were trying to let's draw a little pocket here. Here's a little pocket. This is a really poor pocket. But you were about to finish the game, so you're trying to hit the 8 ball into that corner pocket. There's two things that you need to do. You need to hit this ball hard enough that it'll knock the 8 ball into the corner pocket, but you also need to hit it accurate enough that it's not going to hit the 8 ball off in some other direction and cause you to lose the game. So those are the two things that are necessary, and that's called collision theory. Collision theory. And that's everything that we're talking about today. When we talk about reaction rates, we're honestly talking about collision theory instead. So, as we've talked about, we kind of talked about this point already. As you increase the concentration, there are more particles in the same amount of space. And that means particles are more likely to collide and therefore more likely to react. So, this is just another example showing that. Why does increasing the pressure? So we said with gases, what we want to do is increase the amount of pressure. And what that does is this picture does a really good job of demonstrating that is it forces the molecules to be closer together, meaning they are more likely to collide and more likely to react. They don't have as much free space to operate in. And so the only thing that they can really do is collide with one another. This is talking about the surface area. If the solid is split into several pieces, the surface area increase, and that means that there's more area for the reactant particles or more area for two molecules to collide. The smaller the pieces, the larger the surface area, and that means more collisions and a greater chance of reaction. This piece here has a low surface area but a lot of volume. These pieces have a really high surface area but a much smaller volume. And then the last thing here is catalysts that we'll talk about. Again, I said that catalysts could also be termed an enzyme. Enzymes, I said, were usually in living things, but calling it a catalyst or an enzyme, 90% of chemists will know what you're talking about. This graph down here, this is one that you will commonly see throughout the rest of your high school career. This little EA, so what this means, that is the activation energy. And the way that it works is a lot of times, and especially when you get further in your high school career, you'll talk about a bunch of different types of energy. And so you just use a capital E to represent, hey, I am talking about energy. The little a here, what that represents is that just tells me what type of energy I'm talking about. So in this case, I'm talking about activation energy. Maybe I had ET like this. That might be thermal energy, for example. So you just use the little subscript to describe, like, hey, this is what type of energy I'm actually talking about. With this graph, this activation energy right here, those 2 points that I've circled, that is the amount of energy that I said you need to pull yourself out of bed and go urinate in the bathroom, in the toilet, so that you don't pee your bed and pee your pajamas and have to change your sheets in the middle of the night. If you have a catalyst, it takes much less energy to complete the reaction of peeing. And so when I was doing my internship, the example that I used is this is running to the toilet, running to the toilet. It takes more energy. But what if we could actually pee in the bed and it wouldn't create any problems? And so, what if we were wearing a diaper? Wearing a diaper. Then we could just pee in our bed and it would not be the end of the world. It would take much less energy. We're still using some energy to pee, but it would take much less energy. And in this case, the catalyst would be the diaper. That was the example that I used in my internship. I was young and maybe a little bit stupid, but that's okay. So some examples of catalysts that you will actually have come in contact with. So nickel, my personal favorite element for no specific reason, is a catalyst in the production of margarine. It helps with the hydrogenation of vegetable oils. Iron, that's a catalyst in the production of ammonia from nitrogen and hydrogen. Ammonia is in a lot of the cleaning products that you use around your house. And then platinum is a catalyst in the catalytic converters, that's a confusing sentence, of car exhausts. And it catalyzes the conversion of carbon monoxide and nitrogen oxide into carbon dioxide and nitrogen. And so this helps your cars be a little bit more eco safe, I guess would be the best word of describing them. So catalysts are huge for industries. If you think about, let's say, even the Alka Seltzer industry, they want to make a bunch of Alka Seltzer tablets. If it takes 5 minutes to make one Alka Seltzer tablet, they're not going to be making very much money. They're wasting a lot of time. But what if they could add a catalyst in and have it take 3 seconds to make an Alka Seltzer tablet? Well, now they're making way more money and being way more profitable with the time that they're actually taking. So that's why catalysts are so important for industries. It speeds up all of the reactions that they need to have occur. The other thing it does is it reduces the need for really, really high temperatures. Um, so one of the ways that potash can be mined is potash can be mined through very, very hot and very, very cold water. But that takes an absurd amount of energy, and not to mention that when you're pumping really hot and then really cold water underground, there is the potential for some explosions and some nasty effects. So instead, they can use catalysts to help get the potash, the pure potash, out of these rocks. And they can use those catalysts to speed up the process, but also make it more energy efficient. This bottom sentence says catalysts are also essential for living cells. Biological catalysts are special types of proteins called enzymes. I think there was one last slide. Nope, that was it. All right. Does anyone have any questions about reaction rates from today?